So this is just a quick overview of predictive policing. I want to talk a little bit about crime hotspots, what they are, and then data science and how it can be used for policing crime hotspots. And then I want to spend a little bit of time talking about issues around fairness and privacy in predictive policing, and then end with kind of future directions and what role technology can play in policing in smart cities. So here is a movie of heat maps of crime in Chicago. I'm not going to go into the details here, but essentially what I like to mention is that crime hotspots will form in a neighborhood. They'll stay there for a while, and then they may disappear, and another one may move somewhere else in the city. And these sorts of patterns are ubiquitous in large cities around the world. So let's zoom in on one of these hotspots. This is my neighborhood when I lived in San Jose. So we had a pot club move into the neighborhood, and it was burgled. And then about a week later, somebody's guitar was stolen from their car, parked in the street. My Schwinn bicycle was stolen from my backyard maybe a week or two later. Or I got the order mixed up. I think that's the guitar there. And then finally, like maybe a week after that, a hammock was stolen from somebody's porch. And so you had this string of 5 or so crimes in the matter of a month or two. And then, several years went by, we didn't have any more incidents. Why do these sorts of patterns happen? Well, there's a book called Burglars on the Job, and where burglars have been interviewed. So this burglar here is saying that I go back to the same place because once you've been there, you know the surroundings, you know when people are at work. You might even go back on the same day of the week and commit another crime. So you have these clusters, especially in property crime, that occur because burglars will replicate success. Now, in terms of data science, you're never going to predict that first burglary very well. I mean, you can't predict that a marijuana dispensary is going to show up there, and you can't predict that it's going to be burgled. But what I will tell you is that you can pretty well predict that you're going to have a higher chance of this sequence following initial burglary, because you know somebody's in the neighborhood operating, and you know that people tend to try to replicate success. So there are types of models you can use to model these sorts of clustering patterns. Point processes were developed in statistical seismology, and essentially they model this sort of contagion quality in space-time events. So you have an initial earthquake, then you have aftershocks around that earthquake, similar to how property crime clusters form. And so there are models that will capture the statistics of how these clusters form, and you can use those models to rank a city each day or each shift for police. Each neighborhood in a city has a model that is modeling the intensity or rate of events in that neighborhood. And then what you can do is you can rank neighborhoods by your model and then send police or other resources into those areas to try to prevent crime from happening. So we've run some randomized controlled experiments in Los Angeles and Kent in the UK, where we borrowed these statistical seismological models and applied them to urban crime patterns, in particular property crime in those cities. And what you find, these sorts of hotspot policing experiments have been replicated in other cities, is that if you can send officers into these high-risk hotspot areas, which are about 1% of the city, you can reduce the crime rate by maybe 30% if you can spend a few hundred hours in these hotspots a week. Typically, burglars and other offenders that commit property crimes, if they are deterred in a specific neighborhood they operate in, they don't tend to go somewhere else in the city where they don't have a lot of information. So you get a net crime rate reduction. We also ran some experiments on the accuracy of these algorithms versus human analysts that were tasked with kind of directing patrols before we got involved with the LAPD. And it is kind of an interesting experiment. It's probably not going to surprise any of you, but the algorithm was 2 to 3 times more accurate at flagging these hotspots than humans. So that kind of gave buy-in to the LAPD to use these sorts of algorithms in their daily patrols. Okay, so that's great. You can predict crime. You can maybe prevent some crime from happening, but this is the right brain talk. So I thought I would go into some areas of predictive policing that aren't so cut and dry. So in particular, I want to talk about fairness. And I'll start by not talking about predictive policing, but just fairness in general in machine learning. I don't know how many saw this news article in New York Times or somewhere related, where you had image classification models trained on data sets that ended up being biased. Did anybody see this? Few people. So I mean, basically what happened is you were just talking about kind of the bias of your sample, right, with tornadoes. So in this case, you have a biased sample where maybe you have almost all white males in a training set. And you've trained your convolution neural network on it, and then sure enough, if you go and inspect it, then it's very good at classifying white males, not so good at people of color. And Microsoft released this particular model, and nobody on their research team figured this out. It was somebody else, an MIT grad student, that found that. So it's not obvious that these things are going to occur, but they certainly can happen. And when you start making decisions based on these models or recommendations, then there could be consequences. Another example that I find interesting, how many people know word Tyvek? A few people. So the way word Tyvek works, it's a neural network model for text mining. Each word basically gets represented by a vector. And then you can do algebra with those vectors. So in particular, if you take the vector for Paris minus France, then the closest vector in your data set is London minus England. So you get like analogies out of these word vectors. But somebody else pointed out with these standard word Tyvek models, you also get something like the second line here, right? So you have man minus woman equals programmer minus homemaker is surgeon minus nurse. Now, there's nothing wrong with the ImageNet model I talked about on the previous slide or this word Tyvek model. But there's something inherent in the data set that these models are interacting with that brings these things out. So when we're going to use these in our applications that we build, we have to keep these things in mind. So let's bring it back to crime. So how does this work in predictive policing? So there's an interesting paper recently by Lum and Isaac, and they performed kind of a thought experiment and then used some simulated data. So when you think about how data is collected in policing, it starts with a suspect or a victim, right? So my bike is stolen, I create a report. Probably nothing wrong with that data. But other events in a police database are caused by interactions. So for example, drug arrests have a lot of discretion involved, whether the officer chooses to arrest somebody for a drug crime. That goes into the database, and then that feeds into a predictive algorithm. Now, we're using these seismological models in our previous example that increase the risk of crime if an event happened there yesterday or last week. So now we're more likely to send patrols to that area the next day. Now, if biased arrests are feeding that algorithm, you can get a biased feedback loop with that sort of model, which is what Lum and Isaac pointed out. This is really an open question in machine learning right now, as how you deal with bias. How do you detect bias? How do you mitigate it? And I think it's in its early stages of development. So there's a lot of work to be done, and you probably need a right brain involved to do this. We've done a little bit of research in this area. So we went back and looked at our experiments in Los Angeles. We did not detect bias in that experiment, and I think one key difference between our results and Lum and Isaac's is likely the type of crime. So property crime, only about 10% leads to arrest. Most property crimes go unsolved. So there's a lot less potential for discretionary biased arrests in that sort of data set. There's also some work that we've done and other people have done on how do you mitigate bias in predictive policing or other areas. Essentially, in machine learning, right, you want to fit your data as close as you can with your model, but at the same time, you can add constraints. So, for example, we want everybody in the community to get equal amounts of patrols. And there's a trade-off between fitting the data and achieving that balance, and then you can have a parameter that kind of slides between the two. So this is ongoing work in terms of fairness. Another area I'm interested in is privacy. I live in the neighborhood pretty close to here, and I scraped some data from Nextdoor. There's a lot, Nextdoor, you know, if you haven't been on it, it's a lot of people selling couches or suspicious behavior in the neighborhood. There was one post where like somebody was complaining about their neighbor across the street walking around naked in their house. And their address was, you know, in the post. So like they basically outed, you know, their neighbor on Nextdoor. So I was thinking about privacy around that sort of data. And also, you know, police have these sorts of things like crime tips, but you could imagine if you're an immigrant right now, you're not going to report things to police, or you're going to be a lot less likely to. So how can we maintain people's privacy but still allow them to make these sorts of posts? So we've developed some methods to do this. For example, I want to extract what this post is about without taking the person's address or personal identifying information into the cloud. And how can I do that? So privacy-preserving machine learning, essentially what you do is the model lives on the cloud. And then instead of people sending you data to the cloud, they check out the model client side, and then they do a little gradient descent update on that model with their own data, and then they send it back to the cloud. And so you can imagine applications where you would want this sort of model. It also adds kind of a layer of transparency where this model is publicly available. People can check it out, and then whoever's owning that model can use it, but they're not owning the individual's data. So that's another interesting area that I think has some applications to predictive policing. Okay, so the last thing I want to talk about is kind of where are we headed, at least in terms of my research group's work. So we have a grant from NSF to do work on what's called social harm and predictive policing. So really, police spend only a fraction of their time dealing with crime. So in our city, they respond to drug overdoses. They have to deal with traffic. They sometimes play the role of social worker. And there's also a lot of other agencies in the city that also interact with these certain populations and these types of events that you have to deal with. So our project is around how do you kind of bring in all these heterogeneous data sources from, for example, EMS or police, other city databases, and how do you kind of synthesize all this data and then get it to the right people for the right interventions. And Indianapolis is pretty innovative in some of the things they do. So already they're doing things like they'll pair a paramedic with a patrol car in certain areas where they've had a lot of opioid overdoses to distribute in the naloxone to reverse the effects. And you know, this is a big problem, right? So if you can quantify the cost of social harm, traffic accidents, crime, it's about $1 billion a year for Indianapolis. But using data science, you can actually kind of boil all that down to 1% of the city is where where a large percentage of that $1 billion cost occurs. So we want to kind of intervene at the right places and at the right times. And who should be involved? Well, it's maybe not just police, but it could be even the community itself. So in Nextdoor, you know, that I had that example with package theft. So you might not even need a police patrol. You might just need neighbors to be more vigilant in their neighborhood about bringing their packages inside and looking out for that sort of thing. And part of that project is we have another experiment we're planning to run within the EMS. So basically predicting when and where accidents and medical emergencies are going to occur, and trying to do some dynamic resource allocation so that they can more quickly respond. Now, kind of bringing it back to fairness, 5 years ago we would have just done it, right? But now we really want to be careful. Like, if we change how the ambulances in Indianapolis are allocated, what populations are going to be affected? Maybe we reduce the average response time, but is that going to be fair across everybody in the city? So these are analyses you kind of need to do when you're doing data science and affecting people's lives. So I'll just thank my colleagues and collaborators that have worked on this project, a number of people at UCLA and Georgia Tech and at IUPUI. And then we've had support from the National Institute of Justice and the National Science Foundation. So I think that ends it.